India can launch rockets to the space. India can land on the moon. India can design its own fighter jets. So why can't India build one machine that every advanced air force takes for granted? A fully indigenous fighter jet engine. A program launched in the 1980s, still not powering frontline fighters in 2025. Thousands of crores spent, 40 years of experiments, yet the Kaveri engine remains stuck just short of the front line. Today, using only verified documents and official reports, we break down what really happened and what India's engine story actually reveals about the country's technological evolution. If you see, the Kaveri didn't appear out of nowhere. The story truly begins in 1959 inside a small workshop in Kanpur. 8 engineers and 20 technicians were told to explore gas turbines, technology India had never built before. By 1961, they had run their first tiny turbine. It wasn't meant for a fighter jet, it wasn't meant for anything operational. It was simply proof that India could make a gas turbine spin. When the center moved to Bengaluru and became the Gas Turbine Research Establishment, in short GTRE, the real groundwork started. Through the 1960s and 70s, Indian engineers weren't building fighter engines, they were learning. They were upgrading the Marut's RD-9F, which was actually the Orpheus 703 manufactured by a British aero engine manufacturer. So our engineers were building an afterburner here, a compressor upgrade there, slowly absorbing the fundamentals. The first true sign of ambition came in the late 1970s with the GTX 3714U demonstrator, a small turbofan that proved India could design and test its own core even if it wasn't powerful enough for a fighter jet. Then came 1983, the Tejas program, a moment of national ambition. By 1986, DRDO was authorized to build a homegrown engine. In 1989, the Kaveri project was sanctioned, 382 crore, a 93-month timeline, and a dream of matching the best engines on earth. It was bold, it was courageous, it was also far more difficult than anyone imagined. But every conversation about Kaveri eventually hits the same question. Why not just buy a G engine and reverse engineer it? Reverse engineering is blocked on three fronts: legal, technical, and geopolitical. First, let's talk about ITAR. It's America's International Traffic in Arms Regulation. This places fighter jet engines among the world's most heavily guarded technologies. When India buys F-404s, the contract explicitly forbids opening them up for copying or sharing internal details. Violating these clauses isn't a trivial breach, it exposes India to sanctions and immediate supply cutoffs. So, legally, that path is a dead end. Secondly, even if India could open an engine and study it, modern turbofans cannot be copied by just measuring parts. The real secret lies in the things you cannot see: the internal microstructure of a single crystal turbine blades, the alloy chemistry, the heat treatment schedules, the cooling channels carved inside each blade, and the advanced coatings. None of this can be reverse engineered by shape alone. Without mature materials ecosystem, a copied engine would fail in minutes. And third, after the 1998 Pokhran nuclear test, India came under a broad technological denial regime. Whatever limited design, guidance, or software access GTRE once had from Western firms evaporated overnight. Testing abroad became harder, metallurgical data froze, even computational tools disappeared. So, no, India couldn't just open up a GE engine and learn from it. Legally impossible, technically meaningless, geopolitically blocked. So, to understand why progress was so slow, we need to understand GTRE's reality. Around 2008 to 2010, the peak of the Kaveri program, GTRE had about 240 scientists and 400 technicians. By international standards, this is an incredibly small team for a fighter engine program. Western programs often engage thousands of specialists across design, simulation, metallurgy, manufacturing, and testing. So, India wasn't lacking intelligence, it was lacking human bandwidth. The skill gaps documented in official reviews paint an even clearer picture. Predicting creep life, that is how turbine blades deform under heat and stress, remained a major challenge. A compressor rotor failed around the year 2000, took years to fully resolve. The FADEC, which is the digital brain of the engine, never reached fighter grade reliability. Coatings worked in labs but weren't industrially mature. And perhaps the most crippling limitation was infrastructure. India had no high altitude test facility for decades. Every time GTRE needed to simulate high altitude performance, the engine had to be shipped to Russia, creating long wait times and limited test hours. At the same time, sanctions forced GTRE to develop its own computational fluid dynamic tools. Western tools were no longer an option. This meant rewriting and validating complex fluid dynamics models from scratch, adding years to the development cycle. Everything India needed, material, software, test beds, team size, was incomplete, and building all of it simultaneously was incredibly hard. Many Indians point to ISRO's Vikas engine and ask, if we can build this rocket engine, why not a jet engine? Because the two engines operate in completely different worlds. Vikas, based on the French Viking engine, runs for just a few minutes during launch. It doesn't really deal with thousands of thermal cycles. It doesn't contain turbine blades spinning inside at 1500 degrees Celsius gas flow. It was built with formal technology transfer and it isn't expected to last thousands of hours. Whereas a fighter jet engine like Kaveri, on the other hand, must survive years of operation, tens of thousands of cycles, rapid throttle changes, extreme heat, extreme cold, enormous mechanical stress. It needs to be internally cooled, single crystal blades, it needs industrial grade coatings, it needs advanced electronics and engine control that work perfectly. It needs a domestic supply chain that can cast, coat, and test every part. So, in short, rocket engines gave India the confidence. Jet engines demanded an entire ecosystem. India simply didn't have it yet. So, despite the headlines, Kaveri did achieve meaningful progress. GTRE built multiple prototypes. They logged thousands of hours of ground tests. A prototype even flew on a testbed aircraft abroad. Parts of the engine reached TRL 6 to 7, meaning they worked reliably in relevant environments. But when it came to powering Tejas, the gaps became clear. Kaveri's afterburning thrust plateaued around 81 kilonewton, when Tejas needed closer to 85 kilonewton or more. The engine weighed about 1235 kg, roughly 135 kg over the target. Creep life of turbine blades wasn't yet proven at fighter grade, and the FADEC didn't meet the redundancy and reliability needed for frontline combat engines. That meant one thing: Kaveri couldn't get into the Indian fighter jet. But the story doesn't end there. Kaveri didn't fail, it evolved. India made a strategic pivot. Instead of forcing Kaveri into Tejas, GTRE is now developing a dry variant of Kaveri without afterburner tailored for the Ghatak Stealth UCAV. This variant needs less thrust, has simpler requirements, and it fits the engine's strength. It has already been cleared for in-flight testing, new funding has been committed, and private Indian companies are slowly joining the supply chain. At the same time, India is finally building its own high altitude test facility near Bengaluru, something missing for decades. And the partnership with Safran, a French company focused on aerospace, is opening doors to critical technologies for the next generation AMCA engine, including work on single crystal blades and high temperature materials. At the first time, India has a realistic roadmap, a stepping stone engine for UCAVs and a collaborative path to future fighter engines. So, what does Kaveri story really show? That India tried to build a world class fighter engine with far less money, far fewer people, and far weaker material infrastructure than the countries that succeeded before India could do it. That sanctions mattered, that missing test facilities mattered, that the supply chain mattered. And yet, India didn't walk away. It built an indigenous core, it built a dry variant for Ghatak, it built new test facilities, it built new partnerships. The ecosystem that simply didn't exist in the 1980s is finally forming today. Building a modern fighter engine isn't a decade long engineering project. From a low technological base, especially under technology embargoes, it can be a 50-year national mission. India is now deep into that journey with clearer eyes, better tools, and more realistic goals. That's all for this video. If you like this video, please do subscribe and share it with your friends.